Hello, this is Chris Contalupo. Today in this video I'll be presenting tutorial 4. Tutorial 4 is similar to the last tutorial, tutorial 3, but we're injecting imbalance in a different way in tutorial 4 by inserting a spin loop rather than adjusting the amount of work that needs to be done. So first thing I want to do is to get the run started because it takes a little while to go. So we're setting our MPI exec as follows with a mask that identifies one CPU for our controller and 15 CPUs for each of the application ranks on the two nodes that we'll be running. And then we'll execute with the following command where we'll run tutorial 4.sh and we'll be running with 15 OpenMP threads using the MPI exec command line above and with 8 total ranks for the application and 2 for the controller. Okay, so this will run two different versions of tutorial 4 with different configuration files. And so let's look first at the tutorial 4 script. So here in this script, it's similar to tutorial 3. At the top we have this section here where we take one of the hosts and populate this tutorial imbalance conf file um, with the imbalance. And I'll go over that in just a moment. But you can see that this is exported as the imbalancer config, this file that's created, and in both cases here. But as before, we have one run using the governing policy and the other using a balancing policy. So if we look, the tutorial for imbalance config already on disk here. I created it prior to launching this application, so it wasn't chosen at random. I specifically put the imbalance of 10% onto the node Mr. Fusion 1. And how does that work exactly? We have a configuration file here, and it's parsed by this imbalancer. And if we look at the imbalancer.h, it's a very simple interface that's defined here where we can set the fraction of imbalance, and then there's an enter and exit call. And that's actually implemented with the C++ implementation called the imbalancer.cpp. It has similar methods, frac, enter, and exit. And you can see the implementation down here below where we store the fraction we call frac in our local member variable, mDelayFrac. Upon entry, we just record off into the mEnterTime variable, the entry time. And then at exit time, we also take a timestamp and figure out the difference between entry and exit. And then we multiply that difference times the delay fraction that's derived from the configuration file. And then we spin until that delay, that time, which is the fractional delay of the time spent, has been exhausted. Okay, so that's the way that works now, and you can see these are the C wrappers here to the C++ implementation. So the way this this will work in our case is that when we run through the loop, Mr. Fusion 1 will end up spending 10% more time doing dgem than it would have otherwise. So this is similar to tutorial 3, but in that there's a 10% difference, but it's not actually doing the dgem work in this difference. It's doing this spin loop. So if you look at, for instance, the difference between tutorial 3.c and tutorial 4.c, you'll see that in one case we split based on rank, that's in tutorial 3, then we defined a different size problem. In tutorial 4, we're simply calling this enter and exit API around the dgem call. We can look at that very specifically in the actual source code. So again, we're calling this dgem static, so that uses the static member or the static memory in order to store the initial values for the matrix multiply. But here around that call, we have an entry and exit call for our imbalancer. Okay, and so we expect to see that node 1 has about 10% more work as in tutorial 3. So let's just take a quick review of a run of the tutorial 3 output. So if we look at the dgem time for tutorial 3, we'll see that um, there's the balancer, again, we showed this in the last time we looked at these output files, causes the runtime to be similar for that policy, and we can see it's quite different for the governed policy where we haven't done anything to balance the work. And we should see a similar output when the run on our left here finishes, which is just completing. And if we look at tutorial 3's output for the outer sink, this is the time for the entire runtime of the application. We'll see that the balancer ended up shaving some time off of the total runtime for the application. So let's see if we reproduce similar results for our other method of injecting imbalance. If we look at the outer sink here, we'll see a similar reduction in time. So here we spend 138 seconds when we're using the governing decider, and we use the balancing decider, the total runtime is trimmed down to just below 134 seconds. And if we look at the time spent in dgem, we see a similar result as before, not quite as good at balancing here, or that is, these numbers aren't quite as close together as they were before, but you see a great improvement over the case where we didn't do any balancing, and we have this big gap between the time spent running dgem on the two nodes. Okay, and again, we can look at the policy. So, that was used, and here's the output, for instance, for tutorial 4, looking at Mr. Fusion 1. We'll see that the policy started at 150 watts and then crept up to 161. And then on Mr. Fusion 2, we'll see that the policy also started at 150 watts but was reduced to 138. Okay, and so what's important to note about this tutorial is that imbalancer API can be wrapped around any workload to inject some imbalance. We have these workloads here in the tutorials that we can scale with this big O, but there are many workloads which do not scale as nicely or as cleanly, and it can be useful to have this sort of method for injecting load imbalance. Okay, next time we're going to go over tutorial 5, and in tutorial 5 we review how we can use the progress API that GOPM provides in order to see the progress through a region be reflected in the trace. Okay, thanks for joining.